Hi. Welcome to the lecture on Chapter 3. This will be the first of two lectures on cryptology, cryptography. And so this one's covering just some of the basics, and then we'll go a little bit more advanced next chapter. So what are we looking at? We're going to look at what the definition of cryptography is, describe some of the different algorithms, hash, symmetric, asymmetric, and cryptographic algorithms. We'll explain different types of attacks, and then we'll list various ways that cryptography can be used. So what is cryptography? Cryptography, basically, it involves three things: understanding what it is, what it can do, and then how it can be used as a security tool to protect the data. Now, what is it? Basically, it is scrambling of information so it can't be read. You probably used it in grade school, in passing notes to your girlfriend or boyfriend. So in this case, it transforms information into a secure form so that what? People you don't want to see can't understand it, can't access it, can't read it. Now, there's another thing that is also out there called steganography, and basically that hides the existence of data. Like on an image or an audio file or video file, you can contain embedded messages, and all that is that it's achieved by dividing data and into smaller packets and then hiding into the unused portions of the file you're trying to hide it. Now you may hide the data in header files that contains a description field between sections of the metadata. Now, metadata is data used to describe the content or structure of the data, but not necessarily a message that you wanted to pass on. So just kind of showing you how the hidden data is all inserted. So I've got a message to be hidden. I create a binary form of it, insert it in an area between metadata header files, so that now I've got a message hidden in this picture of the Statue of Liberty that nobody can detect. Now, so what is cryptography? There are several key terms you need to be aware of. One is encryption, and basically that's just changing the original text into a secret message. Decryption is sending it back to its original form. You're going to see the term plain text. Plain text is unencrypted data to be encrypted. So it's basically your original message that you wanted to encrypt. Now, the ciphertext is scrambled, unreadable output of the encryption. And then the third one, another type, is clear text data. It's data that's stored or transmitted without encryption. Some of the older wireless technology security methods sent all data as clear text. So it meant you could just go out, look at it, observe it, capture it, and you could read everything that needed to be, that you wanted. We don't try to do that very much anymore. Hope not. Now, plain text is input into the cryptographic algorithm. That cryptographic algorithm is also called the cipher. And it consists of procedures based on mathematical formulas used to encrypt and decrypt the data. Now, one of the things that this mathematical formula uses is a key. It's a mathematical value entered into the algorithm to help produce that ciphertext. And of course, the reverse, you use that same key to decrypt. Now, there's two different types of ciphers out there. There's a substitution cipher, which basically substitutes one character or another. And there's a couple of different types. One type is ROT13, which an entire alphabet is rotated 13 steps. Letter A actually is the letter N. Or there is the XOR cipher, and it's based on the binary operation exclusive OR when it compares two bits of information. So here's a diagram that you've got plain text, that's your message you want to create. You've got the encryption algorithm. With that algorithm and the key, I create the ciphertext. The ciphertext is transmitted, goes into the decryption algorithm with that same key, and comes out with the same author. So that's on a high level, that's the process that you're going to see. So plain text into the cipher, using the cipher, output as a ciphertext, transmitted, and both of them use in decrypting and encrypting use a key that needs to be transmitted. Now here's just a couple of examples of the algorithms. So here's your alphabet numbers across the top. Substitution, here I'm going to substitute, the numbers for letters. So it ends up being, word security ends up being that numerical string. The ROT13, does that rotate 13, so the A goes to N, gives you the numeric. So security ends up being a graphic or unreadable string. And the XOR cipher, it does an exclusive OR on the 2 bits. So an exclusive OR by definition is 0 and 0 equals a 0. 0, 1 or a 1, 0 ends up being a 1. Both 1s end up being a 0. So I do that comparison, and then gives me do that XOR operation for the result. So here you've got 2 different combinations, security, compared. You got to compare it to something. So I got another word I'm comparing to. I'm going to compare it. It's got to be the same size, at least same number of characters, and I match up, XOR each one of those, and come up with a number and insert that there. Now, modern cryptographic algorithms rely on mathematical formulas. And basically, a lot of them depend on the quality of a random number. Otherwise, no identifiable pattern or sequence. And the software that generates that is a pseudo number generator. You may see it in the text PRNG. So it's pseudo number generator. And all it tries to do is generate a sequence of numbers whose properties approximate those of a random number. It says approximate because some of the older versions, if you run it often enough, it wouldn't give you a random number. You could get it to give you the same number back. Now, 2 factors that thwart threat actors from discovering the algorithms. One is diffusion, and the other one is confusion. Diffusion is if a character of plain text is changed, it should result in multiple characters of the ciphertext that's changing. So you got to make sure it goes to more than one character. Confusion says the key does not relate in a simple way to the text. So it's just making sure if you use those 2 threats, it will help minimize that. Now there's 5 basic protections that cryptography tries to perform. 1, it gives you confidentiality, ensures only authorized parties can view the message. Integrity, makes sure that the message is correct and unaltered. Authentication, it ensures that the sender can be verified. Non-repudiation provides that the user performed an action. So it proves that somebody do something to the data. Obfuscation is basically something that makes it obscure, unclear. So we're trying to do some of these protections in every message. So you may hear security through obscurity. It's an approach in security that where virtually any system can be made secure as long as outsiders are unaware of how it functions. So that's kind of what we're trying to do. We're trying to make sure that you don't know how security is being provided, which then says, I probably can't get there. The disadvantages kind of really obscure everything from everybody. Probably depends on how bad what's inside and how much somebody's willing to pay. Now, just to give you characteristics and descriptions and what kind of protections can be done, this chart shows you the different characteristics and how it could be done. So confidentiality can be encrypted information only viewed by those with the provided key. Integrity, it can't be changed without, except by the ones that have the key. Authentication, just proof the sender is legitimate, not an imposter. Non-repudiation says individuals are prevented from fraudulently denying that they were involved in the transaction. And then obfuscation says, hey, I'm hiding details that nobody else can determine. Now, cryptography can provide protection data that resides in one of three states. One, data that's in use, and that's data action being performed by endpoint devices. Your phone, your computer, could also provide data in transit. That means that when it's being transmitted across the network, whether Ethernet, wirelessly, or data at rest, when it's actually data stored on electronic media. That's on your disk drive or flash drive. Now, there are definitely some constraints to this. One, there's the number of low-power devices, small electronic devices, has grown significantly. And, of course, these devices need to be protected. And also, applications that require extremely fast response time causes problems, or gives us a constraint as far as the amount of data that we can do, what security method I'm going to use. Now, based on resources and security constraints, it's always a tug of war between available resources like time and energy and the security provided. What is important that there's a high resiliency to cryptography. It's the ability to recover quickly from these constraints. This gives you a nice picture as far as how much energy it takes, how much delay, how secure you want to be, how much power is generated. So there's all this balancing act that how much security you want to put in, what method you're going to use, as far as how do you want to protect your data. Now, there are some fundamental differences in the type of algorithms, in the amount of data processed at time. There's a stream cipher, which takes character and replaces with another. There's a block cipher, which manipulates an entire block of plain text one at a time. And then there's a sponge function, which takes an input string of any length and returns a string of any requested variable length. So those are three different types of algorithms that we can provide. Now there's three categories of the different algorithms. There are hash algorithms, symmetric and asymmetrical algorithms. Now hash algorithms they create a unique digital footprint based on the set of data. And it's the process is called hashing. It is basically, this is a fingerprint, is called a digest. Some kinds of message digest or hash represents its contents. The contents cannot be used to reveal any of the original data set. And it's primarily used as a comparison purposes. Now, hashing was intended to be one way that a digest cannot be reversed to reveal its original set of data. Now, there's some algorithm characteristics. One, it's got to be fixed size. Short or long data sets have the same size hash. Unique. Two different data sets cannot produce the same hash. Original, the data set cannot be created to have a predefined hash, and it's got to be secure. The resulting hash can't be reversed to determine the original text. Now, hashing is often used to check, verify the contents that you've downloaded has not been changed. And when you download some software off the internet, sometimes you'll see a hash sum number similar to what you see here, to say that way you know it's unique, that one. So somebody can say, okay, what's the hash of Kali Linux 64? And that number should be identical, to make sure that if that number is different, if you download it and it doesn't match that, you probably got some integrity issues that you needed to take care of. Now, there's a couple of different hash algorithms out there. There's a Message Digest 5, MD5. It's well known. Has a message length padded. It takes the message length and pads it to 512 bits. So based on whatever size it is. Its weakness, in a compression function, it could lead to collisions. So it could be that the two data points aren't matched. So some security experts recommend using a more secure hash than MD5. Those of you who've been in the networking class, you probably saw Cisco was using some of the early days MD5 as setting up some of its secure network. Now, the secure hash algorithm, SHA, is more secure than the Message Digest version. Right now, version 2 of SHA is currently considered to be a secure hash. SH3 was announced as a new standard in 2015, and it may be suitable for those low power devices. So we'll just have to wait and see how that plays out. Now, there's another one that's called the Race Integrity Primitive Evaluation Message Digest. It's a mouthful, but it's basically it has two different and independent parallel chains of computation. So the results are combined, and the results are combined at the end process. So there's several versions, 128, 256, and 320. So just know that one's out there. And it's also the hashed message authentication code. It's providing improved security. It uses a shared key possessed both by the sender and receiver, and the receiver uses the key to decrypt the hash. So let's now take a look at some of the symmetric cryptographic algorithms. And basically, symmetric cryptic algorithms use the same single key to encrypt and decrypt a document. Some of the original algorithms out there was called private key cryptography, or PKC, and where a private key was kept private, supposedly between sender and receiver. Now, some of the common algorithms used today are, you've got data encryption standard, DES, triple DES, advanced encryption, so it's AES, and there's definitely several other algorithms out there. But basically, what do I have? I got my plain text, I got my encryption algorithm, here's my key, create the separate key, but the key is identical both on the transmission and the receiving. So the private key, they're identical. Now, what do you think the risk is of these? How private do you think? Gee, I can't remember my key, so I'm going to keep it on a Post-it note and put it on the back of my keyboard. Secure? Think about it. Now, data encryption standard DES is based on the product originally designed early in the 70s. It used a 56 key and is a block cipher. It was okay, but triple DES was designed to replace DES, and it uses 3 rounds of encryption. So the ciphertext of the first round becomes the input to the second becomes version of the third. Most secure versions use different keys for each round. So you got 3 rounds, 3 different keys. Makes it difficult. Here's just a graphic of plain text, 3 different keys, 3 different rounds, giving it the different message. Now, advanced encryption standard, AES, is a symmetric cipher developed about 2000 as a replacement of DES. It performs 3 steps on every block, every 128 bits of plain text. It was designed to be secure well into the future. There are some other algorithms out there. Just take a look at those. Each one has its pros and minuses. The trouble is the weakness of symmetric algorithms is distributing and maintaining a single secure key among multiple users, especially if they're distributed geographically. Now, an asymmetric cryptographic algorithm is known as a public key cryptography. It uses 2 mathematically related keys, the public key available to everyone and freely distributed, and a private key known only to the individual to whom it belongs. So here you got public key, private key, same message, but 2 different types of keys. So one everybody knows, one that only, in this case, Alice knows. Oops. Now, there's some important principles. You got public key, private key, and key pairs. You got to make sure that those 2 are related. And remember, keys can work in both directions. So those are some key things you want to keep in mind. Now, some of the common algorithms, you got RSA, elliptic curve cryptography, digital signature algorithm, and those related to key exchange. Now, the RSA algorithm was done in 1977, patented by MIT in 83. Most common asymmetric algorithm out there. It uses 2 very large prime numbers. The elliptic curve cryptography, users share 1 elliptic curve and 1 point on the curve. It definitely uses less computing power than the prime number. Its key sizes are smaller, and it's considered an alternative for private number-based for mobile and wireless devices. So it may have some benefits. So here's your elliptical curve, and you got a couple of different data points. So you keep those in mind and say, hey, that's how I can tell the difference. Now, digital signature algorithm, DSA. Digital signatures, you've seen it before. You've signed documents probably electronically. Basically what it does, it verifies the sender. It prevents the sender from disowning the message they sent, and it proves that the message it proves the message integrity. So it kind of gives you a little picture here. Here's the text, here's the hash algorithm, gets your digest, goes into the asymmetric key, Bob's private key, and now on that private key, we're going to take the message and I'm going to put a digital signature on it, transmit it, so that at least that when Alice receives it, she knows Bob sent it because he signed that letter, that thing. Now, so now I got this key that I got to share. The question is, there are different solutions in that for that key exchange. Under normal in-band, so what can go across the network, you've got the Diffie-Hellman, imperial, elliptic curve, Diffie-Hellman, and perfect forward security. All these are different types of how to exchange the key. Now, so like I said, that's a big issue. Now, what are some of the common attacks? And some of those include target algorithm weaknesses. So I'm looking for weaknesses in the algorithm, or I'm going to exploit when things collide or things get delayed in implementing things. Now, the method of attacks can focus on circumventing some of the strong known cipher attacks. Maybe I can downgrade. So when I can convince somebody that, gee, I know you're on version X of a particular study, can I convince you to go down? Can I maybe not convince you, but kind of trick you into downgrading to a lesser secure protocol that has weaknesses. Maybe I can use weaker algorithms or take advantage of maybe not properly implementing the algorithms, because all these algorithms take work to implement correctly, and if I want to be lazy, I can cause a problem. Now, known cyber text attacks, statistical tools attempt to discover a pattern in the text. And that way maybe they can reveal the plain text or the key itself. So there's several different options out here. Let you take a look at those. Now, the downgrade attack, basically the threat actor forces the system to abandon a higher security mode of operation and falling back and implementing older, less secure. Using depreciated algorithms means use an algorithm that should not be used because of its known vulnerabilities, or improper implementation, which is also known as misconfiguration implementation. Because it has several different configuration options, unless careful consideration is taken, you can leave yourself open to security breaches. Now, when two files have the same hash, it is known as a collision. And a collision attack is an attempt to find two input strings of a hash algorithm that produce the same hash result. So you're going to keep trial and error to find out I've got a known, and maybe I stole the packet with a hash on it, and I'm just going to keep churning back here trying to find an attempt to find that algorithm based on trying to reproduce something that has identical hashes. Another attack is the birthday hack. Now, based on the birthday paradox, which says that there will be a 50% chance that someone in a given room shares your birthday if there's 253 people in the room. So they try to say, hey, if I give you enough attacks, enough attempts, maybe I'll find that combination quicker. Now, what can I use this stuff on? Now, like I said, we just said earlier, we want to make sure we're going to use it should be used on data in transit, data at rest, and when possible, data in use. This includes individual files, databases, removable media, data on mobile devices. You can do this both either via software version or hardware version. Now, through software, you get file-on-file system cryptography. And that means I can encrypt or decrypt files one at a time, or one by one, encrypt one file. Or I can use a pretty good privacy, PGP, and it's widely used for asymmetric system. It uses files and emails on Windows system. You've got a privacy, GNU Privacy Guard, and the Open PGP are alternatives that can be used. But they're pretty good. They use block stuff. Now through software, operating systems, Microsoft, all of them have some kind of software that's part of their operating system to encrypt data. So it's used based on the file system. It's tightly integrated with the file system. And encryption and decryption are transparent to you as long as you're allowed to be on that machine. And then full disk encryption protects all the data on a hard drive. BitLocker can do this, and that's also included in Microsoft. It encrypts and decrypts an entire system volume, including the Windows registry. So you can protect yourself quite a lot. Now, software encryption is subject to attack by exploiting its vulnerabilities, like any other security issue. Cryptography can be embedded in hardware, which provides a higher degree of security applied to USB devices and to standard hardware devices. Now, some of the options are Trusted Platform Module or the Hardware Security Module. From a USB device encryption is based on flash drives, it can be used. I think one of the labs that will do, I guess we're not going to do that. I keep forgetting which lab I assigned. But you could have encrypted your USB. And then you have the secure encrypting device drives, and it's encrypting hard drives to protect all files stored on them. So those are just two of the ways that can be done. Now, the Trusted Platform Module, a chip on the motherboard provides all these services. It includes a true random number generator, done entirely in hardware, so there's not subject to any software attack. It definitely prevents computer being booted in files, data that's been offered, and it prompts for a password on the hard drive. Hardware Secure Module. It's a secure processor. Includes onboard key generator and key storage facility. But it can be used across the LAN. So in this chapter, you just kind of got a high level of brush of what cryptography is, pros, types, what types there are, what types of algorithms exist, what you're trying to, whether it's a hash or symmetric or asymmetric, whether it's, through hardware or software, and how it cannot, so all of those are things that just kind of help you get a grasp on the material today. If you have any questions, feel free to ask.